Today we're going to talk about something that I find to be a little challenging for students the first time. And I've kicked around different ways to present this. And keep coming back to the same way that I want to present it because it makes the most sense to me. We're going to talk about angular momentum conservation again. But we're going to talk about the motion of a point mass. This particular example applies to a large group of situations and can explain a ton of phenomenon. But it doesn't seem like it's like it applies to rotational inertia, but it does directly. For example, one of the best examples of this is how momentum is transferred from a baseball bat to a baseball. You guys have all watched somebody hit a baseball before, but when you swing a baseball bat, the baseball bat has angular momentum about a pivot point through the center of the batter's body. But that transfers into linear momentum in the baseball during the collision. So how do we mathematically bring these two things together since they're different measurements for sure? Angular momentum and linear momentum aren't at all the same measurement. And so that's what we're going to talk about today. And this applies to not just baseball and a bat, but golf ball and a golf club. All these share the same kind of transfer of angular momentum, even though the golf ball and the baseball in both circumstances leave with only linear momentum. So I'm going to go to a problem that we've already been working on. Let's talk about the merry-go-round because it's a good example of where to start. And in this problem, I want you to imagine that guy that was in the video. Now, when he wanted to get the merry-go-round to spin, he simply walked up to the side of the merry-go-round and applied a force to it. And that caused the merry-go-round to spin because that was an external torque that was acting on the merry-go-round. And that external torque caused the merry-go-round to spin, and then he jumped onto it. In fact, I think he ran around the outside edge, and he provided an external torque. But if you've ever been a child before, and I hope some of you still are, and you've been to a park where there might be a merry-go-round, one of the other ways to get the merry-go-round to go is you just take a good running start at the merry-go-round and jump on it. Anybody ever done that before? Not enough of you. That's too bad. But it can be fun. Actually, the truth is it's still fun. If you haven't tried it recently, you should. It's a blast. I did it just the other day. But there was also swings at that park, so I went and got on the swings instead. But what I'm trying to say is that if you take and you run directly towards the merry-go-round and then you jump on it, the moment you and the merry-go-round join together, you both end up having angular momentum after the jump. But the question is, did you have angular momentum before the jump? You're traveling in a straight line towards the merry-go-round. Now, the answer is clearly no. It doesn't appear that way, but that's not the whole story. First, let's make sure that we handle a few of the little details that I think you probably already know, not because you're so great at physics, you're getting there, but because you know things about the park. For example, is it pretty clear to you that when you're running towards the merry-go-round, you would like to land on the edge? That will make the merry-go-round spin. Is it kind of clear to you that if you run towards the center of the merry-go-round and jump on it, that you're not going to get anything spinning on the merry-go-round? So you're aware of the idea of where you landing on the merry-go-round having some bearing as to whether the merry-go-round will spin afterwards or not, correct? So we know there's something to do with not just how you're running, but the direction you're running as well. Now, what's actually happening here, and I won't say actually happening, what physicists have decided as a means of observing this is that the person, although they have linear momentum, and let's be quite honest, the truth is when the person lands on the merry-go-round, they apply a force to the merry-go-round right here at the edge. That force causes a torque on the edge of the merry-go-round. It's probably friction or them holding onto the handle. But to understand how much force there is, we have to find a way of getting the inertia of the runner to be a part of the problem when it becomes the inertia of the system. And so what we say is that a point mass does have angular momentum. We use a lowercase script L for this version of angular momentum. This is the angular momentum of a point mass. And we state that the angular momentum of a point mass is equal to how far away from the axis of rotation they are and how much momentum do they have. It's a cross product because the angle at which they are approaching makes a difference. Now, to put some labels to this, R is going to be this yellow arrow, and P is going to be the white arrow. And because this is a cross product, R cross P is R times P times the sine of the angle between them. So this is the angle between them. So as the person runs at the merry-go-round, we say that this is how much angular momentum they have, even though they're just traveling in a straight line. Now, you guys who are taking notes, if you truly want this to sink in and you want to have an understanding of what's happening here, this person's angular momentum only really matters because they are going to jump on the merry-go-round. If there's no merry-go-round there, they don't really have angular momentum. Their angular momentum exists because of the situation in which they find themselves. So what I'm trying to say is that if you take away the merry-go-round, so literally just take it away, there's nothing with which to compare the person's motion with. This R no longer exists because there's no merry-go-round here. They just have linear momentum. The reason we say angular momentum exists because the merry-go-round is there. But it still seems a little weird because it's not like they're actually traveling in a circular path. They're traveling in a straight line. But imagine that you, this person's friend, are already on the merry-go-round. And let's say that you are watching them. Well, as they run, let's say they don't jump on, they just keep going. Is it clear that if you were watching them, this red arrow or this red line represents your line of sight? Does it look like, from your vantage point, that red arrow is traveling in a circle past the merry-go-round? As they're observing it, wouldn't your head have to rotate to follow them? We say that their rotational rate is based on how this red line rotates about the axis of rotation. So although it doesn't look like they're traveling in a circular path, if you're observing the person from the merry-go-round, they are traveling as you would perceive them as a circle as you go around you. Does that make sense so far? A little bit, maybe? It doesn't seem, I know it's weird, but if you had to watch them pass by the merry-go-round, you would have to sweep in an arc to observe them. The rate at which you would sweep your head around to observe them represents the rotational rate relative to the merry-go-round, even though they're just traveling in a straight line. That wouldn't exist if they were traveling directly towards the center. Meaning, in this problem, if they were traveling with a momentum that was straight at the center, would you have to rotate your head around to observe them? Well, they're coming right at you, right? So there'd be no rotational rate associated with them coming right at you. This only exists because they're going kind of at an angle relative to you. Go ahead.
If you were spinning and the person was running straight, then what would that look like? Like, what if the person in the middle wasn't still and they were on spinning?
Well, I don't know. That'd be weird, wouldn't it? But that wouldn't affect their angular momentum. And the reason it doesn't affect it is because even if let's say that the merry-go-round has a spin to it already and they're standing on it, their motion isn't based on how the merry-go-round is moving. Their motion is based on where the axis of rotation is, and that's a fixed point in space. Does that make sense? Now, there's a little more to this, and some of it's subtle, so let me make sure I handle some of the subtleties. When they jump on at the edge, they do apply a force to the edge of the merry-go-round. But the merry-go-round doesn't change position because the merry-go-round is rooted to the ground. So although they apply a force here, there's also a force here from the pivot point from the ground. So the net force of this collision will be 0. But because this force is at the edge, the net torque isn't 0, and that's why the merry-go-round spins. But it's very difficult to calculate that force. It's not difficult to calculate their momentum. And so in this problem, if we want to figure out how fast the merry-go-round is going after the kid jumps on it, we can set the angular momentum before the kid jumps on it to the angular momentum of the system after the kid jumps on it. Since there's no external torque, the system's momentum should be conserved. So that would mean that the angular momentum of the kid would eventually equal the angular momentum of the kid merry-go-round system. So there's a future where the kid is standing here and the merry-go-round and the kid are spinning. So if this is the before, this will be the after. So afterwards, we will have angular momentum. And this is going to be the moment of inertia of the disk plus the moment of inertia of the person times omega. This suggests that we could figure out how fast a merry-go-round will be traveling after the kid jumps on it. But keep in mind, this would also be able to tell us, say, how fast a baseball is going depending on how fast the baseball bat is swung. It can work in the opposite direction. So if the baseball bat has angular momentum before the collision, well, the ball is going to have angular momentum after the collision. And therefore, we can do the same kind of calculation, but in reverse. Same way, if the kid is on the merry-go-round and it's spinning and they jump off, we could also calculate how fast they will be moving due to them jumping off. All these kinds of problems are handled by dealing with angular momentum. But there's a problem with this, and it's not an obvious problem because you're just thinking, okay, so all I need to know is a couple of things and I can calculate angular momentum. I need to know how far away they are, I need to know how fast they're going, and I need the angle. And I could calculate the angular momentum. But if you're paying really close attention, you realize this R and this phi are transient, right? They only exist for an instant. Isn't the R getting smaller all the time? And isn't the angle getting bigger all the time? That, in my head, would suggest that maybe the momentum is changing all the time as they get closer and closer to the merry-go-round, but that wouldn't make sense if they're traveling at a constant speed. How is this working? So I want to show you something because this is not actually how we would normally calculate it. We're going to use a shortcut, but I want to explain how the shortcut works, okay? It's going to involve a little bit of trig. And I know that this is already a little confusing, but you'll understand why we want to use the shortcut when we see it, okay? So I'm going to redraw this, and I want to be very careful about the way I draw it so I can elucidate the point. Here's our merry-go-round. The axis of rotation ends up being our point of reference. It's important because all of this takes place only because there's an axis of rotation in the problem. I'm going to do something else. I'm going to put a tangent line here so that we have a point of reference. This line is tangent to the edge of the merry-go-round. We're going to say that our person is running with a momentum this direction along this tangent line. At this instant, if I keep staying with our nomenclature, there's going to be a value for R here, R1, and an angle here, and I'll call this phi1. And they're going to have a momentum that is constant as they run towards the merry-go-round. So right now, their angular momentum would be R1 P sine phi1. Is that okay so far? Any questions about that? Seems pretty obvious. So then we advance a few seconds. They're still running at the same speed, but now they are closer. This will be R2. This will be phi2. So their new angular momentum is R2 P sine phi 2. Now, this is enough examples for me to demonstrate something to you, but you imagine I could put up a bunch of these, right? I want you to observe this very carefully. I'm going to draw a couple things. First, I'm going to draw a triangle because I see an implied triangle right here. Do you guys see that? In this implied triangle, there is this point here, that the radius of the merry-go-round. If I look at the radius of the merry-go-round, I'm going to notice that it's related to phi 1 and r1. Do you guys see the right triangle that's there? So sine of phi 1 would be opposite over hypotenuse. You see, I'm just looking at geometry right now. We okay with that? All right. Let's draw another triangle. You see this triangle? It's the other where the person is a few seconds later. If I do the same thing, look at sine of phi 2. Is it clear that it's going to be r over r2? Okay, so far? Are you noticing that r equals r1 sine phi 1 and it equals r2 sine phi 2? Do you guys see that okay? This r represents the point of closest approach. If we look at just the kid running, they are eventually going to make it to this location where they are running tangent to the edge of the circle. Do you guys see that okay? So there is an L that has R, P, sine 90 degrees. Is it clear to you that all of these have to be equal? Because this one is actually R1 sine phi 1 times P. This one is R2 sine phi 2 times P. And this are both R. So when we calculate angular momentum for a point mass, we don't usually care where the kid starts. We care where the kid actually interacts with the merry-go-round. That's all that matters. Now, in this one, it's kind of nice because the kid's jumping right on at the edge. But we will always use the angular momentum of closest approach. Where do they land, not where do they start? Because this is a collision. And just like we talked about with collisions first semester, a collision is always the instantaneous moment before the interaction and the instantaneous moment after the interaction. So there's the instant just before the kid hits the merry-go-round, and then it'll be the instant just after they interact with the merry-go-round. Let me show you how this example would work, okay? So let's consider a problem, a collision between the kid and the merry-go-round. So I'm going to draw just two things, the merry-go-round before and the merry-go-round after. Just before, I have the kid running towards the edge of the merry-go-round at 3 meters per second, mass of 70 kilograms. And the merry-go-round is the same merry-go-round from yesterday, 2-meter radius and 200 kilograms. It's a disc. So this will be before. Afterwards, the kid lands on the merry-go-round, and the merry-go-round and the kid both begin to rotate. So this represents our collision. All good? Following along so far? Now, I'm not going to tell you where the kid started. I don't need to. I am going to tell you that the kid is going to jump and land on the edge of the merry-go-round. That's what you need to know. So, when we start considering the conservation of angular momentum, the kid is the only thing with angular momentum before the collision. And the merry-go-round and the kid will have a combined angular momentum after the collision. Now, believe it or not, I'm going to think about after the collision first, because this is going to be the moment of inertia of the merry-go-round plus the moment of inertia of the kid. They will be one thing, and they together will be spinning. That one's pretty easy to consider, isn't it? And I think since we did part of this problem yesterday, you would agree that this will be 1/2 mr squared for the merry-go-round and mr squared for the kid because he's a point mass, all times the angular speed. And if I still continue this with our values we have, 200 was the merry-go-round's angular momentum, right? 1/2 times 100 times 2 squared. This kid is different. We didn't have a 70 kilogram kid, but I'm using what I used in first period. So this person is 70 times their distance away, 2 squared. So that's 70 times 4, so 280. Yeah. Yeah, I'm sorry. If we're using yesterday's merry-go-round, it was 100 kilograms. So let's stick with yesterday's merry-go-round. Sorry. Try to stick consistently from one day to the next, and I just got a little overzealous. Now, we want to deal with the kid now. We don't know where the kid started, but we know that the kid's going to jump on at the edge. So in our heads, you just take and advance the kid to that instant they're jumping on. At that instant, their value for R and P and the angle are all kind of set because we're advancing them right to the edge, so R becomes the radius where they jump on. P is their momentum, which is just going to be mv, 70 times 3. And since we advanced them to the edge, it's a sine of 90, which is just 1. Well, 70 times 3 is 210, times 2 is 420. Keep going. So 420 kilogram meter squared per second is the angular momentum of the kid just before the collision. And this has to equal 480 omega. Now, just to keep the units a part of this, 480 is kilogram meter squared times omega. I'm doing that so that when we do the division, you'll see how the units behave here. You'll notice that when we divide, the kilograms will disappear and the meter squared will disappear, leaving us with 42 over 48 nothings per second. If the units cancel out and you know it's something that's spinning, what unit do you have? Radians. So this is a radian. Now 42 over 48 can be reduced down to a decimal. That's no big deal. Like I said, in this instance, he's running not at the very edge. He's running towards a point in the middle. So that does make it for a more complicated geometry. But there's also problems like this, and this one is a little bit weirder, so bear with me. By weird, I mean it's just it takes a little bit of imagination. Imagine you have two pucks coming at each other, and they have Velcro on the outside of them so they can stick together. There's a line that exists that's something you have to kind of create that exists in this problem, where these two objects are going to come and strike each other. So that's going to happen when they make it to the center. So there's this point of contact right there, where they will connect because they got some Velcro between them, and suddenly they're going to be spinning. Now, it should be clear, the momentum of this system is zero, right? The total momentum of the system, because momentum's a vector quantity, mv for this puck and mv for this puck will cancel out if we just add them together. Do you guys see that has to be true? However, there is clearly, I don't want to do that. There's clearly a line, oh, Mr. Shelton. There's clearly a line here that connects the center of the rotation with the center of the puck. Right? The point between them will be with the axis of rotation. There is no fixed point, because that point doesn't exist until they make contact with each other.